blood. You got to have it. You need it. It's almost like the information superhighway. Now, does anybody have a problem with me saying that? The blood and the circulatory system is like information superhighway?
No. Nervous system.
Huh?
Nervous system.
The nervous system is half. What's the other half of the control that we just finished chapter 17 on that transports in the blood?
Endocrine.
Yeah. No, I was hoping you'd walk into that one. Yeah. So your nervous system is information superhighway. Your blood vessels are information superhighway because of the hormones that we just put in them in the endocrine system. But it does so much more. And when we look at the blood, there are a number of components in the blood. The formed elements. This is going to be the cellular stuff, either cells or cell fragments. And we got that swimming around in fluid that has dissolved molecules in it, a lot of proteins. We got a lot of electrolytes in it, our sodium and potassium and calcium. We've also got glucose in it. We got other proteins that are there just in case you cut yourself. We have immune proteins in there to protect you. There's so much stuff in the blood. And it's going all over the place. We have dissolved gases, oxygen, carbon dioxide. Here's a little preview. Where is oxygen transported in the blood? Red blood cells bound to hemoglobin. Here's the tricky one. Carbon dioxide is transported, dissolved in the plasma as bicarbonate. Only about 15% of the dissolved carbon dioxide is bound to hemoglobin. Most of it is processed by the red blood cell, but converted into bicarbonate, which helps to buffer the pH of the blood. That's then transported back to the lungs, where the red blood cells reverse the process, turn it into carbon dioxide that dissolves out and you exhale. But it's not the red blood cells doing the most of the transport of CO2.
So something cool that I saw as an EMT was that patients coming from house fires, right? So what you would see is you put the oxygen sensor on them and they would read as having fine oxygen levels, but in reality they wouldn't, right?
Right.
Because the CO and actually the CO2, if there's too much of it, can remove the oxygen from the red blood cells and blood to the hemoglobin instead.
Oh, it's mostly the carbon monoxide.
And it gives you like a false reading.
Carbon monoxide sticks to the hemoglobin and it won't come off. Oxygen can't compete it off. So you're suffocating even though you're able to ventilate.
Yeah.
Wow. Nutrients. We said glucose, right? We said hormones, right? Endocrine system. Heat. Do you recognize that your blood vessels can regulate your body temperature? In the summer, and I really have to apologize for complaining about how hot it was in the summer, especially when we just had 10 and 11 degrees. Okay, that serves me right. In the summer, when you are so hot, the way you cool yourself down most appropriately without trying to throw your body into shock is you run cold water over your wrists. Because look, if you look at your wrist, do you see all of the blood, the superficial blood vessels, especially the veins, right there? That is a place where you dissipate a lot of heat. I used to see this in a lot of the old NFL films, but I just saw it last week, Kansas City playing Buffalo. Travis Kelce took off his helmet, and they've either got the camera on Travis or Taylor, right? So, but he took his helmet off and the steam just coming off of his head. Your head loses a lot of heat. That's why if you are out in the cold, put something on your head. Because the blood vessels, when you're too hot, the blood vessels are going to dilate to the skin and release that heat. When your body is too cold, there's some areas your body, the blood vessels are going to completely close off. And if you don't warm yourself quickly enough, those parts of your body are going to turn black. And now you've got what? Frostbite. So that's absolutely how the blood vessels are going to help control and dissipate heat. Waste products. Certainly we got our nitrogenous waste that the kidneys are going to filter out. But carbon dioxide is a waste product that we're going to get rid of in the lungs. So all of that's being moved around on this superhighway that we call the bloodstream. So the blood also regulates. We just talked about body temperature. Body pH, I touched on it just a little bit. See, here's CO2. And in your red blood cells, you have an enzyme that we're going to talk about. It's called carbonic anhydrase. Carbonic anhydrase takes water and CO2 and converts it into carbonic acid. That quickly breaks down into a hydrogen ion and bicarbonate. Those ions are shipped out into the blood. And it's that bicarbonate then that can buffer the pH of your blood. So, regulating pH. Fluid balance. Aldosterone, atrial natriuretic peptide, angiotensin, all of these things are going to be important for regulating fluid balance. But your blood vessels are going to play a role in this as well. And this is going to be sort of a factor of your blood pressure and the solute concentration of the blood. Yeah, we're going to get back into the tonicity. You remember hypertonic, hypotonic, isotonic? We're going to get back into that, especially when we talk about what's happening down at the capillaries. Protection. Your blood is protecting you. Your white blood cells and this other component that's not an actual cell, it's a cell fragment called a platelet, they're going to be protecting you. So we have immune system cells. Here's a white blood cell that's crawling around and all these little black things are bacteria. That one's going to gobble it up. Man, got that like a Shipley's donut. So protection. They're your platelets. We also have proteins, inactive clotting proteins present in the blood. You need them to be inactive, right? You don't want the clot to happen just any random time. You could have a stroke if it did. But these proteins are there so when you do have an injury, they can be activated quickly so that you can start the process of clotting the blood sooner than later to protect yourself from blood loss. Okay, let's just go over some vital stats of our blood. On average, you have 5 liters of blood circulating in your body in this adult. Typically, males have a larger volume of blood than females. Now again, when we say male and female, we're talking XX and XY. The biology is not sociology, so we're just going to leave it at that. Largely, when you're working in a clinic, and I don't mean to be insensitive at all, but this is just the world you're going to be living in. When you have someone come into the ER, you're not worried about pronouns. You're worried about their biology. And in this particular case, men are going to have a higher fluid volume in their blood, and they're going to have more red blood cells. Because typically, with an XY male, they have a greater volume of muscle mass in their body that requires more transport of oxygen. Now, you know that's a generalization, right? Because there are times when I go into Planet Fitness, there's a whole lot more beefed up females in there than these big heavy duty, beer belly guys. So that's a generalization, and that's all we can do with the textbooks and our information. All right? About half, a little over half of your blood, and this is overall, your blood is water. Half of the volume of your blood is going to be cells and platelets. And we're going to see that in the plasma, about 90% of your plasma is going to be water. There's our physiological neutral, just on the basic side of 7. I think chemical neutral is 7.000000. Yeah, we're at 7.35. And then when we go back to our tonicity, osmolality, and this is milliosmoles. 300 milliosmol is the osmolality of your blood. Why is that important? You're going to be putting fluids into your patient. You need to understand why certain fluids are going in and why there's this stuff written on those bags. The concentration of your sodium chloride, the concentration of your sucrose solutions, those things. They're balanced so that they are isotonic with the blood of your patient. So they're going to be at 300 milliosmol as well. So formed elements, the stuff in the blood, either cellular or derived from cells, and we've got our red blood cells, erythrocytes. And I worded this very carefully because I put O2 and CO2 exchange, because I didn't say transport because of the CO2 thing. They enable the exchange between the air and the plasma, but they don't directly transport CO2. Red blood cells do directly transport oxygen. White blood cells collectively are called leukocytes. And we've got quite a few of those that we'll get into. Platelets are called thrombocytes. Now, platelets are produced early on, and they have a fairly short lifespan in your body. So that's why I don't know if any of you do the plasma giving, but some of you give platelets, because people that need those that have problems with platelets. Platelets are produced by this humongous cell that's multinucleated in the bone marrow called a megakaryocyte. And these are cellular fragments that just break off. They're membrane-bound bags of enzymes, and they're going to aid in blood clotting. One of the first steps in stopping bleeding when you've got a vascular injury is forming a platelet plug. Because when a platelet sticks, it's going to cause a positive feedback mechanism that's going to make other platelets sticky, and they're going to stick together, and everything's going to stick together, and hopefully you plug the hole a little bit until at least you can form a clot, which is going to close everything off.
You said they're membrane-bound what?
Bags of enzymes.
Thrombocytes are?
Thrombocytes, yeah. I mean, there's no nucleus, no organelles. They're just phospholipid, cellular membrane wrapped around bags of enzymes.
What can kind of affect the rate of like thrombocyte production, or just like how well they actually form clots?
The rate of their production, I think that's probably going to be based on your overall fitness level, your overall health level. As you look at malnourished individuals, geriatric individuals, everything's starting to slow down. That's the first thing that comes to mind. I'm sure there are blood diseases that affect platelets and not others. Certainly problems forming platelets is going to lead to a bleeding disorder, but there are a lot of things that can happen that can cause that as well. So when you look at the percent of your blood that is formed elements, and principally the red blood cells, because they're going to be the biggest component of your formed elements, versus your plasma, that's a measure called your hematocrit. And the way it used to be determined is you would put a portion of blood into a centrifuge tube or one of the little capillary sticks, a little glass capillary rod. They stick it into a centrifuge, and then they measure what percent of that volume is going to be your plasma, which is this sort of, they call it straw-colored look, this sort of yellowish color. That's going to be the fluid portion. The red portion, the heaviest things are going to go to the bottom when you centrifuge. And the red blood cells with the iron and the hemoglobin is the most dense, so it's going to go to the bottom. The liquid's going to be on top. And right in the middle, that white band, they call it the Buffy coat. That's going to be your white blood cells and platelets. That's where they're going to sediment out there. So when you look at that just based on a volume level, a normal hematocrit is going to be around, well, we're doing plasma. I'm sorry, I'm getting ahead of myself. It's going to be around 45%, which makes 55%, the bulk of that volume is going to be your plasma. Go ahead.
So hematocrit describes the portion of your RBC, so the red.
By definition, they say cells, but when you look at how much dominates with red blood cells, the Buffy coat's just kind of not considered. So it really is a measure of red blood cells, but technically, hematocrit is cellular. Yeah.
Hematocrit is the measure of your
Formed elements, but as you can see, that Buffy coat is such a minor contributor that it's often not even thought. Hematocrit is really unofficially thought of as red blood cell composition. And a lot of times now they just look at the, I think it's grams per deciliter of hemoglobin instead of looking at this. Because they have these machines that can read without centrifugation. They can just, if anybody gone to the blood center, they've got these little plastic manifold looking things that they get your blood draw from your finger stick. How many people think the finger stick is the worst part of giving blood? Me. They can stick that big needle in my arm as long as I don't see it any day. I hate the finger stick. I wish they would stick my finger and then give me a second and then read my blood pressure, because I'm sitting there with high blood pressure just because, oh.
Did you know if they take
I'm as bad as Elf. I promise you. I'm as bad as Elf with a finger stick.
if they take it on your thumb, does it hurt? Can't feel it.
No, it's got to be this middle finger. It can't be this middle finger or any other finger. It's got to be that one. I've done it so much, it's got a callus, I think. If they get another finger, I go, nope, this one. All right, so plasma, fluid portion, the solutes are the proteins, the ions. We've got our coagulating proteins, and we're going to come back with fibrin. What's that last part? Ogen. What does that mean? Precursor, and it's inactive. These clotting proteins, you don't want them active until they're in the right place and it's the right time. We've also got plasma proteins, albumin, that's going to be a carrier. These globulins, the ones we're going to talk about the most are the gamma globulins, aka antibodies, these immune proteins. So those are all components of the plasma, about 90% water. You're going to find that number is going to sort of vary. Some say maybe 88%, 89%. I like numbers with zeros.
So fibrinogen is inactive until you get cut or something, and then it needs.
When you get cut, there's going to be a cascade that's going to activate an enzyme that can clip the Ogen off fibrinogen and activate fibrin.
Okay.
Yeah. But that will only happen at the site of an injury. Yeah.
Going back to platelets, would osteoporosis in women affect their platelet count?
Would osteoporosis in women affect platelet count? Osteoporosis is the lowering the density of bone. You're removing too much bone, but basically you're creating more marrow spaces. So I don't know if just that physical osteoporosis would have an effect. I do know osteoporosis is caused by hormone variations, especially as you get postmenopause. Hormones are absolutely going to control blood cell development, platelet development. One of the hormones, thrombopoiesis, is going to be produced, and I'm not exactly sure what regulates that hormone production. So possibly, I don't have a direct answer.
Okay, I'm just. I don't know.
No, it's okay. That's you're supposed to think.
Negative carrier
Yeah.
sites
Yeah.
in the bones. Or
All right, so there's a normal hematocrit. All right, got your blood spun down. You see the Buffy coat, red blood cells. You see the plasma. Anemia. You don't have as many red blood cells, or you have enough red blood cells, but you don't have the same level of hemoglobin, sickle cell anemia, or other conditions. Thalassemia is a condition where that could happen. So they're going to give you iron. They're going to tell you to eat more protein. It's kind of a problem. Polycythemia. You have a lot of red blood cells. Now we understand anemia, right? You're not transporting enough oxygen. You get winded easily. Well, now you got polycythemia, you've got more hemoglobin, more red blood cells. It doesn't sound like that's a bad thing to me. How is polycythemia clinically relevant?
Sedation of the cells.
Possibly, but something a little more obvious. On the right track. Not enough plasma.
Dehydration.
Too much oxygen.
Not enough plasma. I'm going to tell a story like this. I was raised on sweet tea. Anybody else raised on sweet tea? Somebody puts unsweet tea in my mouth, I'm spitting it out. Especially if I don't know. If it's tea, it's supposed to be sweet, and I'll drink it. If it's unsweet, No, I'm from Texas. My grandmother would make tea on the stove in a pot. She'd put the tea leaves in the pot, boil it, pour it into a pitcher through a strainer, and she would dump in maybe a bag of sugar into that hot tea solution. Why does she do that?
So it can melt.
So you can dissolve more sugar into the tea. Then she would add water. My grandmother's tea was almost like syrup. Why was it almost like syrup? Because of all the sugar. What's wrong with the blood now?
It needs to be diluted.
Don't have enough plasma. Your blood is thick. Your blood is turning into syrup. So what's your heart going to have to do to transport syrup? It's going to have to beat harder. What's going to happen to your blood pressure? Your blood pressure is going to go up. Polycythemia is not some thing to, oh, it's not that big. No, you got to get that fixed too.
You do see that in like severe dehydration though.
Yeah. How can you fix polycythemia?
IV fluids.
Leaching.
Literally blood leak.
Get blood. Yeah. Get blood. There are patients all the time that go to the blood center for therapeutic phlebotomy. They have polycythemia. They have too many red blood cells. We'll take some.
That's funny.
Yeah. Yeah.
Okay, so with anemia, so you know how people eat ice when they're anemic, right? So what does that have to do with?
They eat ice
Yeah.
when they're anemic.
Yeah.
I've never heard that before in my life.
Really?
I'll have to look that up and report back Tuesday. I'm like, you're punking me. What? No, I promise I have never heard that in my life.
A pound of ice.
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 I'll have to investigate that and report back. Will that work? Yeah.
People who live at higher elevations naturally have more of a polycythemia.
I don't know if they have polycythemia, but they've got a higher hematocrit. They do, and that's why athletes do that. And the Tour de France guys, before they started doing all this testing, they would do something called blood packing.
Is that where you freeze your blood?
They would take their own blood weeks and weeks in advance and store it, and then right before a competition, they would spin down the red blood cells and suspend just a little bit of fluid in it, and then give it back to themselves to increase their hematocrit for competition.
That's called blood doping.
I think that's blood packing. There's no dope in it.
Yeah.
I mean, there's nothing they can test for. It's your own blood.
That's crazy.
But it's not fair, unless everybody's doing it. If everybody's doing it, it's okay. Did I answer your question earlier?
Yes, you
Okay.
did.
It's interesting.
Yeah. All right. Some important plasma proteins. Albumins. This is the smallest of all our proteins, and it's the most abundant. Albumin is really going to be important as a solute. You remember that word solute we lose with hypotonic, hypertonic? We're going to see here in just a little bit when we look at the exchange that happens in our capillaries, we're going to need those proteins that as fluid leaves the capillary because of the high blood pressure, the proteins that are present in the blood, that's going to cause the blood to be hypertonic compared to the interstitial space. And so we're going to have an osmotic draw to pull the water back in. It's going to create like a cycle. And albumin is a huge player in maintaining the osmotic pressure. Does everyone know the word colloid osmotic pressure? We talked about colloid with the the thyroid. Colloid refers to protein. Osmotic pressure could be sodium, it could be potassium, those ions. This is protein as the solute, hence that word colloid.
Colloid is the fluid that's inside that cell, right?
It's inside the follicle of the thyroid.
Follicle.
Yeah. Albumins also act as carrier proteins. We have molecules that are hydrophobic. They're not going to like messing with water. So they're going to be insoluble in your plasma. Albumins can coat some of those proteins. How many of you get packages from Amazon? Okay. All the time. Did you really just say that? All the time. Well, my baby just had a birthday, and she always wants to go to Super Yummy. Anybody going to Super Yummy? It's not really a birthday place, but she loves Super Yummy. So it was raining, and I said, "Oh, I left your birthday present in the car." You probably won't find this surprising at all. And when we finished eating, I said, "Oh, let me go get your present. Just bring it in, and she can open it." Okay, she's thinking present, right? No, I had this big, huge Amazon box. And she goes, "Dad, what are you doing?" And I'm like, "It's your birthday present." She goes, "I can't believe." Well, no, actually, I can believe that you would do this. Well, there was a Amazon box, but inside it was the box that her air fryer came in, right? So the Amazon box is keeping porch pirates from seeing what your package is and getting it. Albumin keeps your water insoluble molecules safe because the outer wrapping makes the whole package water soluble. And so that's the function of albumin.
Like, how can albumin change? Does it change the polarity, or it's simply like
It coats it. It just coats it. It's like painting water seal on your deck. Your wood is
how
hydrophilic.
does it attract a non-polar like steroid?
It's not just some attractive force of albumin to the protein. There's some binding, some specific binding that goes on there.
Protecting hormones, and what else did you say?
Hormones and, there's another one. Hugh, you caught me. There's another example that can be protected that way.
Well, go back and listen to it.
Yeah, Hugh, listen to that. I'm sorry?
Hydrophobic.
Albumin is hydrophilic.
Hydrophobic.
Albumin is
But it coats the
hydrophilic.
hydrophobic.
Correct. That makes the whole package hydrophilic. Yeah. Have a good weekend.